Okay, go ahead.
This afternoon's session is moments, and whilst we've only looked briefly, there is a brief snippet on moments. Today's looking at bodies at rest. So we'll just have a look at some of these initial basics, and then we'll go to an exam style question. So let's get this computer working if I can. Okay. Right. So here's a couple of questions just to basically do a warm-up activity. Once we've done this warm-up activity, I'm going to have a look at this particular question which is on a past paper, and then we can compare what we do with the solutions. So we'll have a look at that, and then that will wrap up the show this afternoon. Now, what we've got here is we're told that it's at rest. Now, when it's at rest, it means that there's no movement. And once there's no movement, there's no clockwise, there's no anti-clockwise movement. And so we're going to take a 20 Newton force downwards. And it's we're going to have to state that this is a uniform bar. Therefore, the mass will act halfway. So if this is 5 meters long, at the 2.5 meter mark, there's a force down of 20 newtons. Now that means that the force up at C and at D must add to equal 20 newtons. And they might not be always identical. So let's have a look at the distance here. This distance from here to here would be 0.5 meters. And the distance from the halfway mark to D would be, would that be 1.5? 1.5 meters. What we're going to do is we're going to take moments about one of the points, and let's start by taking moments about C. So we'll just write that moment about C. Now, remember what a moment is. It's the rotation force of force times distance, perpendicular distance away. Now, there's a force here acting at a perpendicular distance of 5 clockwise. And well, actually, if we're going to take moments about C, this force doesn't exist because the distance that force is from itself is 0. But this force here acts down at a clockwise rotation. The distance away is 0.5 and the force is 20 newtons. So the clockwise forces are going to equal the anti-clockwise because that's why it's an equilibrium. Clockwise moment. So the clockwise moment is force 20 newtons times the distance away 0.5 meters. That gives us 10 Newton meters. Anti-clockwise about C is this force here acting on this point at D, and that is a distance of 2 meters from C. Remember, we're taking moments about C. So it's how far is that force away from the point C. This force was 0.5, but this force is 2. And the force is, we don't know that. We'll call the force of D times the distance of 2. So 2fd, and we can find the force at D simply by dividing by 2, 5 Newton meters. So here we have a 5 Newton meter force acting on the bar by the stand. It's not going to move because it's in equilibrium. Because this weight is acting down, this is pushing up, so it's in equilibrium. And they balance each other. Now forces up equal forces down, so total forces acting up will equal the total forces acting down. And we've got a total downward force of 20 newtons. Therefore our force at C plus our force at D is going to be our total force up. If there's a force up at 5 newtons, well, what are we going to have over here? So that's 5, this must be. Therefore, force at C will be 20 minus 5. And that is how we determine what is the force acting on each of these points. Because the mass is closer to C, the force here is greater than the force acting at D, which is further away. All right, so we're looking at clockwise and anti-clockwise being equated because the body is at rest. Let's have a look at the second one and notice how I selected taking moments about C up here. I could have taken moments about D if I wanted to, and then you would have the same answers. You'd have the same answers as this solution here. All right, so let's do part 2. Again, we've got a 20 Newton force acting down. All right, this looks very much. We've got actually, I think this 20 newtons only relates to this question here. Let's just have a look here. There's down X. You know, I don't have the question in front of me. I'm going to assume that what they've done is there's a mass of this in the middle of 20 newtons. Mass always acts at the halfway point of a uniform rod. So no matter what, the mass is going to be acting at the halfway mark. They must have someone standing here, and they must have someone standing here to make sure that this is an equilibrium. And what we've got is we've either got suspending by ropes or we've got some sort of fan here. And I'll call that C and that's D. What I'm going to do is make positions here. We've got a position C, D, and E. Total up equals total down. So 20 plus 20 plus X is going to equal 15 plus Y. Does that make sense? Total up force is going to equal total down force. So we've got 15 plus Y is going to equal 40 plus X. Whatever happens, this has got to be true. Now let's take moments. Look for one of the parts which we don't know. We don't know Y and we don't know X. So we're going to take moments about one of these 2 points. It doesn't matter. Now let's take moments about D. The beauty of that is that force Y times 0 is 0. So it eliminates one of the variables. Let's take moments about D. And that means all the clockwise forces have to equal all the anti-clockwise forces. So have a look at, this is a clockwise force here, and this is a clockwise force at 15 newtons. Those 2 forces are going to equal the anti-clockwise forces, which is this one, and this one. So there's two anti-clockwise forces, 2 clockwise forces. See that? So let's take the clockwise force and equal the anti-clockwise force. Taking moments about D, so the distance from D. Now, if that's halfway, so if that's 1, and it's 1, 2, and 1, it's a 4 metre length, this must be 1 metre from here to here. And then that's going to be 1 metre from here to here, 1 metre. Let's do the clockwise, this one first. That's X times 1. Newton meters. Let's do his clockwise first. That's 15 force times what's the distance away from D? See that distance? What's that distance? We've got 15 times the distance of 2. So 15 times the distance of 2. That's our clockwise force. Remember the moment, just put it up here, moment equals F times S. Force is a Newton and S is in meters. So we're going to get some answer. F is the force, S is the displacement, the perpendicular displacement from that point. So we're going to get some answer in Newton meters at the moment. So the anti-clockwise moment, this one and this one. So force is 20 times the distance or displacement of 1 meter. And other anti-clockwise is a force of 20 meters times the displacement of 1, 2, 3 away. So that distance, perpendicular distance, 3 meters from D. Okay, so that's 30 equals 60. Therefore, x equals 80 over 30. Have I made it out? Yes, I have. I don't think I've got 30. I need more coffee. 80 minus 30. Okay. So we have a 50 Newton, that's X. So we've got 50 down, 20 down, 20 down, 15 up, therefore what will Y equal? Remember, 15 plus Y will equal 40 plus X. 50 now we know X. So we've got 90 down and 90 Newtons up, therefore Y will equal 25 Newtons. Okay. So this is just a warm-up activity for calculating forces that are unknown. And there are 2 forces unknown that we had to discover. X had to be 50 and Y is 75 Newtons. Let's move forward into the question at hand. That was a warm-up activity. And here is our actual exam question. So we're sitting our exam, we look at a question for what? We've got a moment's question. A uniform beam. So uniform beam, when you see uniform, it means that the mass is acting exactly halfway along the beam. So at the 3 meter mark, you've got an arrow down, a force down due to weight of 20 kilograms. So this is going to be 20 G, Newton, down acting up. You could turn it into 9.8 times 20 if you like, but let's leave it as 20 G. The beam rests in equilibrium, so that clockwise equals anti-clockwise. Total up equals total down. So the force is acting. We want to find the magnitude of the reactions on the beam at B. So the reactions is the force acting upwards on that beam through that point C. Now total up, the force at C plus the force at B is going to equal total down force 20 joules. So just keep that in mind. Once you know one, you can find the other very quickly. Well, we will take moments about, either we will take moments about B, because there's an unknown force there, or we will take moments about C, because there's an unknown force there. So let's take moments about B. That means force times displacement from B. And clockwise, the clockwise moment will equal the anti-clockwise moment. So from B, this moment is of acting of the weight from that distance down is an anti-clockwise moment. And the force acting up here at that distance is a clockwise moment about D. So this moment will equal this moment. The clockwise moment is the force of C times the distance from here to here. So if that's 1, this must be 5 meters. And anti-clockwise with this force, 20G, and the distance is halfway from 6, because it's a uniform line, halfway where the force is acting. So that's the therefore, the force of C will be 60G. Now we can divide by 5, which is 12G newtons. You can turn that into a decimal or just leave it as 12G. Did it say? No, it didn't say. If you did turn it into a decimal, you could I would leave it into 1 decimal place, or there's often instructions, but 1 or 2, 1 decimal place is possibly enough for this question. And now that we know the force of C acting up, the reaction of the beam, the reaction on the beam at C is 12G newtons. Therefore, the reaction on the beam at B will be 8G newtons. Reaction at C. So C is 12G newtons, and B will be 8G newtons. Turn that into a decimal. That's worth 5. Not too bad. Now, second part of this question, there's a boy of mass 30 kilograms standing on the beam at D, somewhere along the beam at D. The beam is still in equilibrium. Now, if the boy stands here, chances are it's possible that this bar could tip, but it might still be somewhere you're going to have an equilibrium point where there won't be any tipping points. The magnitudes of the reactions on the beam at B are, okay, so it's what they're saying is the boy stands somewhere so that the reaction on B and C are equal. All right, so we've got the force acting down, and the boy has to stand somewhere in here so that the force at C and the force at B are equal. So the force at C equals the force at B. Let's look at our total equaling total down. Now total up force is the force at C plus the force at B. Because they're both equal, let's give that a value. Let's just call it x newtons. Therefore, we could say x plus x is our force up, and down will be 20 plus 30G. 30 times 12, 30G down, 20G down. So together, x plus x is going to equal 50G. Well, we can already find out, therefore, the force at C and the force at B, 2x equals 50G. Therefore, x equals 25G, 25G. So we know now we've got a force here at 25G, a force here at 25G. We just don't know where the boy is standing. Therefore, let's come up with a new variable and call it y from the end. Y, therefore, this distance will be 6 minus 5. So if there's y meters to that point from this end, then it will be 6 minus y from the other end. take moments about, where would we want to take moments about? Well, where's the unknown? We won't take moments about the boy, or could we? Well, I don't think it matters, because the only unknown is x, is y. So let's take moments about b again, and that means that the clockwise will equal the anti-clockwise. Let's see what happens. X should be the only variable, so it should be what happens. Clockwise. So I do that diagram again. It's getting very busy. Just do a quick sketch here. B, B, G, 30G, Y, and Y. So, the clockwise force about B. This is anti-clockwise. This is anti-clockwise. Here, the force up is the only the only clockwise force. So that's the force at C, which is 25 newtons times the distance away is 5, still 5, because that's 1 and that's 5. Now the anti-clockwise is the mass of the bar. Anti-clockwise, so that's 20G times 3. And 30G, I'm out of space, times the distance, 6 minus 1. And there we have it. That's it. All we have to do is find y. So 125 Newton meter equals 60G Newton meter plus 30 lots of 6s, 30G lots of 6s minus 30G lots of y. 240G G, 25, that's 25. 25? Yes, 25G. Sorry, this should be 25G. So 25G times 5, that's the G. Bring that minus 240G across equals negative 30GY. And that leaves negative 115 G divided by negative 30 G equals 1. G's cancelled, negatives cancelled, and we're left with 115 divided by 30. No, you do it, so I'm going to use it. 115 divided by 30 equals 3.83 meters. 2 decimal places to dictate, and I'll just put 2 decimal places. And that is the distance. Ooh, get this right, from AD, hang on, from A to D. A is where he's standing, is it? Where's A? Let's look where A is. A is void at D, so the void's here. A is there. Okay, well, hang on a minute. I've said it's 3.83 from the end, but the question wants the distance from A to D. Whoops, nearly looked past that. We've not finished yet. If it's 1 meter from, oh yeah, there's A. Oh no, we're right. A to D. Boy's standing at D. A is on the end. Yep, we're okay. 3.83 meters. All right, let's compare what we've done with our solutions. And our answers for part A was we had 12G or 8G. They've given an alternative in decimals, but that's fine. And we were right there. And we've got 25G, which we said was R. They've called it R, 25G and 25G, because total up equals total down. And then 3.8, and we said 3.83. So it's okay. So if we've said 3.83, I don't think that they're going to worry so much about their marking scheme saying 3.8. All right, so this session is predominantly just a revision on moments. Hopefully you can become more confident looking at a question that has a moment in an exam. I suggest you try one or two, and if you are still having trouble, let us know. But the best thing is to practice as soon as possible. Try to find some questions in a test and give it a try. Don't leave it too long, otherwise you'll forget. And enjoy. Stay happy. And I'll just stop this recording.